National Academy of Engineering, the recipient of the 2014 IEEE Neural Network Pioneer Award, and of the 2015 PAMI Distinguished Researcher Award for Computer Vision. Please join me in welcoming Yann LeCun.
Thank you for coming. Thank you to the organizer for inviting me. It's a real pleasure to be here. So I'm interested in AI, like all of you, and perhaps coming through the angle of machine learning, I've been interested in how AI can come about through learning, and which is probably why I've, spent more time in conferences like NIPS and ICML than IJCAI in the past. But I did give a tutorial at IIIAI many years ago on neural nets. What I like about IJCAI, though, is the very wide diversity of topics. This is something that was just talked about. So it's a real pleasure to be here. So almost all the practical applications of machine learning today, what people now call AI, a little, a bit of an abuse of language, but the new AI, if you want, is due to supervised learning. And we all know what supervised learning is. You want to train a machine to distinguish images of cars and airplanes. You show it thousands of examples of each of those categories, and you tell the machine the correct answer, and it adjusts its internal parameters so that the answer you want, the answer the machine produces is very close to the answer you want. And this has been incredibly successful in a host of very useful applications that are very widely deployed and used literally hundreds of trillions of times per day for things like speech recognition, image recognition, face recognition, generating captions for photos, as we just talked about, classifying text into topics, translating, things like that. So what deep learning has allowed us to do is kind of break the old models that date back to the perceptron and to statistical pattern recognition, where the way you have to build your system is by taking the raw data, handcrafting a feature extractor that basically constructs a representation, an appropriate representation of the raw input, so that it can be digested by a relatively simple learning algorithm, like say a linear classifier, nearest neighbor, a tree, or something like that. And what deep learning has allowed us to do is replace this by a cascade of modules, all of which are trainable, and they're trainable end-to-end. So by using simple gradient descent, it's really nothing complicated. We can feed the system with raw inputs, and by appropriately designing the cascade of modules, the modules can not just learn to classify everything, but also learn to produce appropriate internal representations and features to achieve the task. That's really what deep learning was always about. And what's quite surprising there is that the ideas for this go back a long time. They go back to early attempts in the 1950s by people who became very prominent in the AI community of trying to build neural nets. And so what's a little surprising is that you can build those fairly complex systems out of essentially two basic operations. One is just a linear operation. So imagine your system is built out of is basically represented by a vector. You compute weighted sums of the components of those vectors with various coefficients. You pass them through a nonlinear function, and that each of those elements is sort of an elementary classifier, if you want, and you stack many of those classifiers, and that's what constitutes a neural net. So essentially, there's two kinds of operations: linear operations, take a vector multiplied by a matrix, and then pointwise nonlinearities, take a vector and pass every component of that vector through a very simple nonlinearity. In modern neural nets, this nonlinearity is essentially just a half-wave rectifier. So it's very simple. And the amazing thing is that it works at all. So there is an interesting paper by Minsky and Selfridge from the 1950s, where they say, well, this idea of hill climbing, they call hill climbing what we now call gradient descent, but it's the same thing, is never going to work because you're going to get trapped in local maxima at the time, right? Now local minima, but it's the same thing. And so they have this beautiful drawing where, hand-drawn, where you have sort of a peak and a mountain, and then it's surrounded by a ridge, which is in the shape of a ring, and they say you can never get to the maximum because of a ring. So this was an interesting intuition that a lot of people have had until fairly recently, but it turns out to be wrong. In very high-dimensional spaces, it's actually quite hard to have bad local minima. And that's one of the theoretical mysteries of neural nets, which is that when you make them considerably bigger than necessary, they work really well. They're very easy to optimize through gradient descent, and you never have local minima problem. There's a lot of mathematicians and physicists who are, and theoreticians of various kinds who are thinking about this problem, and there's some intuition about it, but it's a bit of a counterintuitive notion. So if you don't put any structure in your system, you just stack linear and nonlinear operations. So what I should say, the way we're going to train this, and I'm sure many of you are aware of this, is we're going to train this through gradient descent, have some sort of cost function that measures the discrepancy between the answer we want and the answer we get, compute the gradient of that with respect to all the coefficients of all the matrices in the entire system, and then take one step of gradient. We do this either sample by sample or block by block, which is the idea of stochastic gradient descent. And one thing we quickly notice is that if we want to apply this to things like images or text, we have to put some structure in the matrices here so that they're not full matrices because the vectors are very, very large. So one such idea goes back, is something I'm associated with, goes back to the late 80s. It's the idea of convolutional networks. And this is a sort of vintage early 1990s convolutional net. So it's been trained to recognize handwritten digits. And what you see here are the various layers in that system. The input is on the left. And then you have the first layer, which is the first column. The operation performed by each of those layers is a convolution, which is a special case of a linear operation. And then a pointwise nonlinearity, which in this case happens to be a hyperbolic tangent. Each of those 6 maps that you see in the first layer has a different set of coefficients to perform the convolution, and all of those are learned end-to-end using gradient descent. And you stack layers of convolutions and nonlinearities. There are special types of convolutions in between that we now call pooling, where all the weights are constrained to be equal, and so that has the property of basically aggregating the response of some filters in an area, and then those are subsampled so as to reduce the spatial resolution of the representation. And as you go up the layers, you get representations that are of parts of the input that are more and more global, more and more abstract, and you sort of force the system to kind of build those hierarchical representations. So we obtained really good results with this in the 90s for handwriting recognition. Why handwriting recognition? That's basically because that was the only thing we could put our hands on, the only data sets for which there was more than a few thousand samples, or a few hundred samples, I should say. And fairly quickly we realized we could use this not just to recognize single objects, but also multiple objects, multiple characters. So and that's going to be important because that meant we didn't need to have a prior pre-processing where objects would be segmented. We could show to the system multiple objects and then train it using sort of a sliding window approach, if you want, to detect individual objects that were centered in a window and then ignore the ones that were on the side. And that system kind of spontaneously can recognize, in this case, multiple characters, but as we'll see later, multiple objects, and also separate automatically figure from ground. So that was working really well. So pretty quickly we built practical systems to recognize handwritten documents, in particular here checks. And by the mid-1990s, we fielded a commercial system at AT&T. This was done when I was working at Bell Labs. There's a company called NCR, which at the time was a subsidiary of Bell Labs that was commercializing large systems for banks to read checks, and they fielded that system. And by the end of the 1990s, the system was reading between 10 and 20% of all the checks in the US. So it's a big success story of the first wave of neural nets in the early 90s. But by the mid-90s, the machine learning community completely lost interest in neural nets for reasons that are not entirely clear. at least not entirely clear to me. Historians of technology will have to explain this one, but partly due to the fact that training those systems at the time was very onerous in many ways. It required a bit of black heart a little bit, and software that had to be written from scratch at the time, that now we can use all kinds of libraries that are open source. Back in those days, open source was not particularly prevalent, and companies were kind of possessive about software. And then there was, very, very few domain areas where there was enough data to train those very large learning models. They all required thousands and thousands of examples, if not more. So that was only practical for handwriting recognition and perhaps face detection and speech recognition, but not much else. And in fact, for speech, it didn't quite measure up with other methods for various reasons. So I actually stopped working on machine learning between 1996 and 2001. I worked on other things, image compression in particular, and came back to it in the early 2000s. In particular with a project with sort of self-driving robots. So this was a small robot. This was around 2003, just when I was joining NYU and leaving industry. I worked together with a small company in New Jersey called Netscale Technologies, and we built this little robot that we trained by imitation learning. So we basically trained a convolutional net to emulate a human driver by being shown the images coming from two cameras in the little truck and recording the steering angle from the human driver, and then the machine would learn to associate one to the other. And turns out this was a very short project, very quick, but it worked really well. And so we showed the result to DARPA program managers who said, this sounds really interesting, let's start a large program on machine learning for robots. And that ended up being what was called the LAGER project, Learning Applied to Ground Robots, which started around 2005 and ended around 2008. So the LAGER robot was built by NREC at Carnegie Mellon. It's a robot like the one you see on the top left. And the idea there that we used was to use convolutional nets to do semantic segmentation. So basically apply a convolutional net to every pixel in an image. So the convolutional net would look at a fairly large patch around each pixel, but be applied to the entire image with a sliding window. It's very efficient to do this with a convolutional net. You can do this very, very cheaply. And then label every pixel as to whether it's traversable or not. So the problem, of course, is how do you collect training data? You're not going to collect a bunch of images and sort of manually label every pixel. But what happens there is that we can use classical computer vision, stereo vision, to figure out if a particular pixel is on the ground or is above the ground using 3D reconstruction, essentially. So that works, except it only works up to about 10 meters. So past 10 meters, there is not enough resolution in stereo from classical baseline and resolution to be able to tell if a pixel is above the ground or on the ground. But that's enough to, even all the pixels within 10 meters, that's enough to train a neural net to figure out what is above the ground and what's not above the ground. So you use those labels automatically collected to train the convolutional net, and then you can apply the convolutional net to monocular data and apply it to the entire image, and it tells you whether there's a path beyond 10 meters. So that system worked quite well. Of course, the robot was completely autonomous, so it had sort of Pentium laptop class computers in the belly, 3 of them. And so we could only run the neural net at about 1 frame per second. So we used it to do long-range vision. And then for short-range vision, we had a low-resolution, 8 frame per second stereo vision system, particularly for handling unexpected obstacles. So system labels the entire image. Then we can map the traversability indices into a map centered on the robot, and then use this map to do planning to go to a particular goal defined by GPS coordinates. So that's the robot in action. The video is accelerated twice, and it's being annoyed by pesky grad students who are entitled to be pesky because they actually wrote the code for this. And so they're pretty sure the robot is not going to run them over. So that was quite interesting and successful. That project ended in 2008, as I was saying, way before deep learning was kind of fashionable. And I can't switch side. Here we go. Oops, I went a little too far, too quickly. What happened next was we realized that this idea of semantic segmentation could be used not just for traversability index, but could be used for labeling every pixel in an image with the category of the object it belongs to. And by 2009 and 10, some data sets appeared with a few thousand images, 3,000 images or so, that were completely manually labeled at the pixel level with on the order of 30 categories. So we trained our convolutional net on this and in fact implemented the overall system on an FPGA, so we could run fast. It could run at about 20 frames per second. And we beat the accuracy record on 3 different data sets. And so we submitted a paper to the Computer Vision and Pattern Recognition Conference in 2011. The submission was in 2010. Pretty sure the paper was going to be accepted as an oral presentation. It was actually soundly rejected by all 3 reviewers, whose main comment was, we don't know what a convolutional net is, and we can't believe that a method we'd never heard of could work so well. In essence. So then I advise my students to not submit further papers that are very sort of heavily slanted towards machine learning to computer vision conferences because it would be a waste of time. But things changed very quickly thereafter. So what happened is that this work inspired a few people, particularly a company called Mobileye, which now belongs to Intel, which is an Israeli company, and they were one of the first to kind of build systems visual sort of vision systems for cars for driving assistance and obstacle detection. And they licensed the technology to Tesla in 2015. The 2015 models of the Tesla S actually include a convolutional net system built by Mobileye. So they were extremely fast in switching from whatever technique they were using before to using convolutional nets once they realized it was working really well. The problem they had is that they had a special chip that wasn't built to run convolutional nets, so they had to shoehorn convolutional nets onto that chip. Nowadays, they have chips that are more dedicated. Meanwhile, other companies jumped on the bandwagon, including NVIDIA and a host of startup companies and larger companies like Uber and Baidu and many others. But pretty much every single vision-based self-driving car system that you see nowadays uses convolutional nets. And that's all because in 2012, our friends from University of Toronto managed to have a very efficient implementation of convolutional nets on GPUs, on graphical processing units. They were getting speed-ups of about 100 over running them on CPUs. And that allowed them to train a very large convolutional net for the time, something with, on the order of almost 1 billion connections, and training them on the ImageNet dataset that had 1.3 million training samples, each of which has an image with a dominant object in it belonging to one of 1,000 categories. And so they stunned the computer vision world a little bit by bringing down the error rate on ImageNet by a large amount. So this was Krzyzewski, Sutskever, and Hinton from Toronto, and Jeff Hinton's group, Yoshua Bengio's group, and mine, and later Andrew Ng's group had been exchanging a lot and working together towards kind of developing new techniques for deep learning and getting things to work. They were the first to have good GPU implementations. So the error rate on ImageNet was on the order of, by some measure, which is, is the correct class among the top 5%. Was around 26% error until, using kind of more classical computer vision methods until 2011. And in 2012, the Toronto group brought that down to a little over 16%. And since then, the performance has improved steadily. The error rates now are below 3%. And that can be done very easily, routinely. Now it can be done, by training in parallel in something like an hour on a network of GPUs. whereas the first version took about a month. There's been this really sort of continuous improvement in performance and a simultaneous increase in the number of layers of those networks. There's an inflation in number of layers in the depth. So in 2013, one of the best performers was the VGG network from Oxford. And then the next year, it was the Google Net from Google. That's a play on the word on the LeNet, which was the name that my boss gave to the neural net we used at the time in the 90s. Then there was ResNet, proposed by Kaming He at the time at Microsoft Research Asia. Now he's at Facebook. And then DenseNet and other things. And those kind of went from, a few layers back in the 90s, 7 or 8, to 12, 13 layers, to 20 layers in 2013, to all the way to 150 layers nowadays. Companies like Facebook and Google and others routinely use networks that are anywhere between 50 and 100 layers for image recognition. So those things are used for image recognition very, very widely. To give you an idea, Facebook users upload on the order of 2 billion photos on Facebook per day. And each one of those 2 billion photos goes through 4 convolutional nets within 2 seconds of being uploaded. One of them just tags all kinds of stuff in the image. Is it a wedding or a party or a birthday party, or is it a landscape or indoor scene or whatever? Or, is there a dog of a particular breed in it? Is there a sailboat? There's a few thousand tags like this that are recognized. The second one does face recognition for automatic tagging of your friends. The third one generates captions for the visually impaired, so there's short descriptions of the image. And the fourth one basically detects objectionable content like violence and pornography. So it's very widely used. There's a lot of compute cycles that are spent running convolutional nets these days, and a lot of work on kind of hardware accelerations for them for that reason. And one might ask the question, why is it that we need so many layers? It's probably due to the fact that the world is essentially compositional. The perceptual world is compositional, in the sense that images are made of little edges or oriented contours, and motifs are made out of assembly of contours, and then parts of objects of assemblies of combinations of those motifs, and then objects are made of parts. And so you have this sort of combinatorial nature of the perceptual world, which applies to a lot of things in the natural world. And so that's kind of naturally represented by multiple layers. And it's always been a puzzle for me to figure out why it took so long to convince the pattern recognition community that having multiple layers was a good idea. Here is a recent experiment done at Facebook which shows that there is a very interesting avenue now where people use supervised learning that is less and less supervised. So this particular experiment was done very recently, where my colleagues took 3.5 billion images from Instagram. These are public photos posted by Instagram users. And whenever people post photos on Instagram, they very often type hashtags to kind of index or describe the content. And so what they did was take the 5,000 or so most frequent hashtags that appear in Instagram photos, and then trained a convolutional net to predict which hashtags would appear for any photo. So it's very weak signal because hashtags, sometimes don't represent anything about the image, but they train this anyway. And then what you do is you chop off the last layer, and then you retrain the last layer, or retrain the entire network, starting from the pre-trained network pre-trained on hashtags. You retrain it on another task, for example, ImageNet or the COCO dataset or some other dataset of this type. And the interesting thing is that they've been able to beat the records on a number of different datasets this way. So there is a big advantage in learning good generic representations with convolutional nets, and it helps to solve any particular task. And either you get better results, or you get the same result with fewer labeled samples. This is a theme that I will come back to in just a minute. But just to complete with kind of the state of the art and the little kind of historical bit, here's some more recent work from Facebook This is sort of a good demonstration of what current computer vision systems can do. This is a system called MaskRCNN, and it does instant segmentation. It's basically a convolutional net, also applied with a sliding window at multiple scales over the image. And it's not just trained to produce a category for what it sees in a window, but also to produce a mask of the object, the dominant object in its viewing window. And it can produce results like this. So it not only recognizes that there are people, but it can tell that there are 7 people, and it actually draws the outline of every person, and you can easily put a bounding box around them, and it detects the baseball and the dog at the bottom, detects the wine bottle, the glasses, the computers in the back, the people, even though you can only see them partially, the backpacks and umbrellas and the almost completely occluded cars, and you can even count sheep, apparently. So it works amazingly well, and people in computer vision, I think, if you had asked them 5 years ago, would have been hesitant to say that we could do this now. But this it's quite interesting. This system is trained to not just outline objects, but also to pinpoint key points on human bodies, from which you can reconstruct sort of a skeleton of a person. And not only does that work really well, it actually works in real time on a mobile device. So what you see here is it's not a fake video. It actually runs at that speed on a smartphone, and it can track a human body in real time and sort of basically reconstruct the skeleton. This is using a sort of mobile neural net infrastructure from Facebook called Café2Go. All of this is open source. One of the good things about Facebook AI research is that most of our research is, all of our research is open. We publish everything, and we distribute most of our code in open source. This whole system is called Detectron, and you can download it and play with it. There's 2 versions, one written in Café 2, which is sort of pure C++, and another one that is written in PyTorch, which has kind of a front end. Another project, this one took place at Facebook AI Research in Paris. It's called Dancepose, and that consists in actually in real time, running on a single GPU at 20 frames per second, slapping a 3D mesh on any number of humans in a video. And again, this runs in real time on a single GPU, so you can change the clothes of someone or remove them, like in this case. This is work led by Natalia Neverova and Yasonas Kokinos, who are research scientists in Facebook in Paris. Now, I've talked about image recognition, but we can apply those things to other domains like translation. And if there's one thing that has been kind of stunning over the years, which is it's been a merging of the underlying techniques used by several different communities. So it used to be that speech recognition, computer vision, and natural language processing were using completely different methods, but now they basically all use neural nets. And many of them use convolutional nets. So this is a system that was developed at Facebook to do translation based on convolutional nets. It's a particular type called gated convolutional nets, which I don't have time to go into, but it works really well. It's also open source. It's called FairSec. And it's kind of a sequence-to-sequence convolutional net. It can be used for other things like text generation and various other applications. So there's tons of applications of convolutional nets and deep learning in general in medical image analysis, in driving assistance or autonomous driving, accessibility, translation, content understanding for search filtering and ranking. I talked about this. Games, of course, and a growing number of applications to science, particularly in high-energy physics, astronomy, and genomics and biology. And of course, everybody would want to build virtual assistants, but they don't quite work. So what's missing there is, we're in an AI conference, and a lot of AI is about reasoning. And what's missing from everything I talked about here is reasoning. It's basically just perception, right? It's sophisticated perception, but it's just perception. So how do we get neural nets to do reasoning? How do we marry deep learning with reasoning, really? And there's a bunch of really interesting work in that direction, augmenting neural nets with memories. which have been done in part by some of my colleagues at Facebook, Jason Weston and his colleagues, something called memory network, where you basically have a piece of the network that is dedicated to being a memory, a little bit like a RAM, except that it's differentiable. And the system can use this as a scratchpad memory if you want to solve particular problems, like, say, hold a dialogue and answer questions about movies. And you know, these systems basically are asked a question, and then they access the memory multiple times and produce the answer. They're trained end-to-end in supervised mode by being fed answers. If you use those models to predict what the subsequent answer of the human person dialoguing with the system is, you can actually accelerate the learning, the training of the system to kind of produce the right answer. So if the system is able to predict what the next answers are going to be, it's able to train itself faster to answer the correct question. Another interesting work in that domain is something more recent also at Facebook. It's a work led by Dhruv Batra and David Parikh on essentially dynamically building a neural net by dynamically assembling modules, trainable modules, differentiable modules, depending on in a sort of input-dependent way. So, for example, you want to ask the system a question like, you show it an image and you ask a question, there is a shiny object that is right of the gray metallic cylinder. Does it have the same size as the large rubber sphere? And so, even as humans, to kind of answer this kind of question, we sort of have to configure or you know, either our frontal cortex or a perceptual system to kind of pinpoint the right features to look at and count the number of objects, figure out if they are near each other. So that's exactly what this does. It actually synthesizes a network depending on the question, which is a combination of differentiable modules that is meant to compute the answer. And the beauty of this is that you can train this end-to-end. You can train the system to actually produce the right set of modules on the fly. And what's interesting about this, among other things, is that what you have is some sort of dynamic network that is determined by program. And so traditionally, a neural net was something that you would define the architecture of in a static way, and then you would just run it and train it. But this thing, you write a program, and then the output of the program, and the program is going to run differently every time it has a different input. And in the background, there is a software infrastructure that figures out how to compute the gradient, essentially, of the output of this program with respect to all the free parameters in it. So that has led some people to kind of call this software 2.0 or differentiable programming. Basically, it's a new way of programming where the instructions are not really completely defined instructions, but they are parameterized modules when you write your program. And then the actual function of the program is finalized by training it on data in any way you want. So I mentioned there is a lot of open source project here. One of them, so PyTorch is the framework that we use at Facebook for deep learning, and it's open source, and it's actually a community project. Facebook is just the main contributor. There's a lot of other systems here, fast similarity search, distributed reinforcement learning. There is actually a sort of professional level Go player called Alpha Open Go that's been built with this, and it's completely open source. And others that I already mentioned. Okay, so speaking of reinforcement learning, so reinforcement learning is really has been making a lot of progress, and we saw this with the prize that David Silver accepted today, and it's really impressive what's happened. But reinforcement learning falls short of learning things at the same speed as humans, as efficiently as humans. And so a lot of the successes of reinforcement learning have been in the domain of games or virtual environments or situations where you have so much data that the number of trials is immaterial, like, say, ranking or things like that. So to give you an example, this is a figure taken from a recent paper from a group at DeepMind, and they have the best combination of algorithms to train a system to play Atari games. And to reach human-level performance on Atari games, the best current reinforcement learning algorithms take about 100 hours of real-time training. It's faster because you can run the games faster, but if you kind of figure out how long it would take if you played the game at normal speed, it would be about 100 hours. And this is to reach human-level performance that a human can reach in a few minutes of playing. So that's quite, quite different. This is not the video I was supposed to show. For some reason, it's showing this one. Anyway, this was supposed to be a video of an agent playing Doom. And RL works really well for games. There's no question about it. And that's because you can run games really fast, faster than real time in parallel. There's a lot of people working on StarCraft these days. It's much more challenging because there's several time scales. But RL is a big problem, or classical RL, or what people call model-free RL. It's hard to use in the real world because it requires many, many trials to learn anything. And if you were to use current versions of reinforcement learning to train a car to drive itself, it would have to run off a cliff a few thousand times before it figures out it's a bad idea. And then probably run off the cliff a few more thousand times to figure out how not to run off a cliff. And this would also apply to running over pedestrians, driving on the left, other things like that. So humans seem to be able to learn to drive with about 20 hours of training for most of us, without ever crashing for most of us. And so we're missing something, we're very fundamental. So what are we missing to get to real AI, really? That's what we're asking. How do we get machines to learn as efficiently as humans and animals? Supervised learning needs too many samples, reinforcement learning needs too many trials, and machines don't have common sense. Common sense is the red herring of AI, if you want. So why is RL the sample efficiency of RL so terribly bad? There is no, most RL systems that we use today have no task-independent background knowledge about the world, like most humans do. They have no common sense, which is a bit of the same thing. No ability to predict the consequences of their actions. They have to try to see if an action results in a good outcome. And no ability for long-term planning or reasoning without actually interacting with the world. So in short, what they lack is world models. If you have in your head a model of the world, you can plan in advance. You can think about the consequences of your action without actually acting and figuring out if the world is happy with it or not. You can kind of run this in your head. And that causes us, the absence of world model, causes us to not be able to build things we want to build. So, we'd like to be able to have machines with common sense because they would be the basis for dialogue systems and virtual assistants that would really help us in our daily lives. They would also probably be the basis for, dexterous robots. We can't actually build robots today that can fill and empty our dishwashers. And we certainly don't have much ideas how to get to general intelligence. So, this problem of modeling the world maybe is a big issue, and that was the title of my talk. So how do humans and animals learn? How do we learn so quickly? So if you talk to developmental cognitive scientists like Emmanuel Dupuy, who is in Paris, they do experiments like the one you see on the top left, where you take a little cart, you put it on a platform, and then you push the little cart. And the car doesn't fall. Of course, it's a trick, it's held from the back, but the baby is being shown this and can't see it. And babies younger than 6 months, look at this and shrug, sure, that's the way the world works, no problem. Babies after the age of 10 months or so look like the little girl at the bottom left. They're extremely surprised that the object isn't falling. And that's because in the meantime, between 6 months and 9 months, they've learned the concept of gravity. They know that an object that is not supported is supposed to fall. How does that happen? So in fact, Emmanuel put together this chart that kind of indicates at which age babies learn various concepts. So things like face tracking happens very early, biological motion, so the difference between animate and inanimate objects, and things like gravity, inertia occurs around 9 months or so. So all of those, what's interesting about this is that most of this is learned purely by observation. There is very little interaction of babies with the world because, before a few months old, they basically can't do anything, right? So they mostly observe, and they amass an enormous amount of background knowledge about how the world works just by watching. How do we do this with machines? And it's not just humans. It's also the case for other animals. So here is a baby orangutan here. And the animation is supposed to play. Hopefully it's going to play in a second. This baby orangutan is being shown a magic trick. And which you're going to see in a minute. Animations are not playing. Oh, well. Oh, it's even worse than this. Okay, my presentation software actually crashed. All right, hang on. Just bear with me for 1 minute. Actually less than 1 minute, hopefully. All right, so I'm not going to show you this animation. I'm not sure why it's not playing. Okay, let's see. All right, so when our model of the world is violated, when we observe something that's unusual, doesn't fit with the model of the world, it makes us pay attention. Sometimes it makes us scared. Very often it makes us laugh. And that little animation of the orangutan was this baby orangutan being shown a magic trick and then rolling on the floor laughing because, it breaks its model of the world. And he's actually laughing. Okay, so here is a concept that might help on the way to sort of get machines to really sort of accumulate a lot of background knowledge about the world, and it's the concept of self-supervised learning. Basically, the idea is to predict any part of an input from any other part. Some people used to call this unsupervised learning. I think it's kind of a confusing word. So imagine you have a snippet of video, and you've observed the past. So the purple stuff is the past that you observe. And the blue stuff is what the machine is supposed to predict. So predicting the future from the past, that's an example of self-supervised learning. And of course, you can wait to observe the future so that you can use this as kind of a training feedback signal to train the predictor, right? But you can also try to predict the future from the recent past. So you kind of pretend that you don't remember the distant past. You can try to predict the past from the present. Pretend you don't remember the past and try to predict what happened, or retrodict what happened from the current state of the world. Or you can try to predict maybe the left half of the image from the right part, or the top from the bottom. Any part of the percept that is occluded or not currently visible, you need to predict, as long as you can observe it at some point. So that's the basic idea of self-supervised learning. Pretend that there is a part of the input you don't know and predict that. And what happens there is that the amount of information you give to the machine, you ask it to predict, is very large now. In reinforcement learning, the amount of data you give to the machine and you ask it to predict is one scalar value once in a while. It's the reward, the value, basically the reward, right? You're not saying anything else to the machine. In supervised learning, you're telling it the correct answer, so it's a few bits. Even when you have 1,000 categories, it's only 10 bits. In the self-supervised learning setting, you're asking the machine to predict everything in the world from everything that it observes. And so it's just a lot more information you're asking the machine to predict, and therefore you can presumably constrain a much larger system to learn much more complex, task-independent stuff about the world. So that led me to this completely obnoxious slide, which has become a bit of a meme in the machine learning community, that if you assimilate intelligence to a cake, the bulk of the cake, the genoise, if you want, is self-supervised learning. That's where we learn everything that we learn. Almost everything that we learn is learned just by observation, by sort of self-supervised learning. We learn a little bit with supervised learning, maybe when we go to school, and we learn a tiny amount through reinforcement learning. And so that is the cake analogy, with reinforcement learning being the cherry on the cake. But note that this is a Black Forest cake, and the cherry is not optional. So this idea of unsupervised or self-supervised learning as being essential is not my idea. Jeff Hinton has been kind of trumpeting this for 40 years or something like that. And I was skeptical at first, but sort of rallied to his opinion in the last couple of decades. And you know, we might ask what self-supervised learning allows us to do, and it allows us to fill in the blanks. And that's a very important aspect of common sense, if you want. So whatever the next revolution in AI will be, it will certainly not be supervised nor purely reinforced. My guess, as a machine learning person, is that it will be based on machine learning, and they will have some component of deep learning, of course. So, you know, could self-supervised learning lead to common sense? There is, you know, a huge amount of things that we infer about the world, and maybe it's based on all the background knowledge about how the world works that we've accumulated. So, for example, if I say a simple sentence, John picks up his briefcase and leaves the conference room, there's a lot that you can infer about John and about the scene. You know, things that, you know, are due to our knowledge of human society, that John is a man, he probably works. But, you know, also things that seem completely obvious, but are not obvious to a machine unless it's learned it. The fact that John is not going to dematerialize from the room, is going to actually walk towards the door, it's not going to go right through the wall, it's not going to fly, you know, things like that, you know, basic things about physics that we've learned. So there's a huge amount of information we can derive from just those few words. And, you know, common sense is what allows us also to interpret pictures like the ones here at the bottom right. Current event just happened yesterday evening. This is President Macron after the French victory in the World Cup. So we need to learn predictive models of the world. And this is something that people in optimal control have been doing for many years. Basically, you have a system you want to control, and you build a model of it. You do system identification if you need to identify parameters, and then you use it to kind of roll out a sequence of commands, and then you optimize the sequence of commands to minimize a particular objective function. That's classical optimal control. And, you know, in AI, that's pretty much the way things should work too. We should have sort of a world model in our head of how the world works, and then we can, in our head, kind of play sequences of actions and see what the result is, and perhaps optimize the sequence of action in advance. That's called, in the context of reinforcement learning, that's called model-based RL. And the problem of model-based RL is that it's very hard to make it work, because it's hard to make models of the world that are accurate. But that's kind of the way you would use them. You would roll out, and then figure out a sequence of action that satisfies a criterion, and for a particular criterion. So in the interest of time, I'm going to skip a couple of things. So the main issue with the world is that the world is not entirely predictable. So if I put a pen on the table, and I show this little video to a machine, and then I ask it, predict what's going to happen next, predict the next few frames in that video, the machine can predict that the pen is going to fall, probably. You can predict that the pen is going to fall, but you can't really predict in which direction. And so our model of the world has to be a model that can predict not just one point, but a whole set of potential plausible futures. And what that means is that this model has to have access to a latent variable that essentially parameterizes this set of potential futures, the set of plausible predictions, okay? So this red ribbon here is a set of possible predictions. There's a latent variable z that you can vary, and when you vary it, the predictor basically spans the entire set. That's a latent variable model. So now what we need is to train this machine is basically an objective function that tells us if the output of the network is on the red ribbon or outside, and hopefully will tell us some indication of in which direction to change the output so that it gets closer to the red ribbon. And the problem is that we don't know what the red ribbon is, so we have to train another neural net to tell us if we're on the red ribbon or not. And this neural net, let's say the manifold of data, of potential plausible future, is something like this in 2 dimensions. What the machine has to learn is some sort of contrast function that looks a bit like this once it's trained, that gives a low energy. Think of it as an energy function. So it gives a low energy to stuff you observe, plausible predictions, and a high energy to everything else. Okay, so as learning goes, for this energy function, it needs to take this shape that it gives kind of low energy to things in the middle. This whole idea of training those two networks simultaneously, that's the idea of adversarial training. I'm sure you've heard of this. And so the idea of adversarial training is that you have the discriminator that basically tells you if you are on the red ribbon or not, if you are on the manifold of plausible predictions or outside. And you train it by showing it examples that comes from data and telling it, make your output small. And then showing it predictions by a predictor, which presumably initially is bad, and you tell it, make your output large. Okay, simultaneously, the generator trains itself to, so what happens when you train the discriminator is that this function takes some shape like this, where the green points are pushed up, the blue points are pushed down. And the generator is simultaneously being trained to bring its green points closer to the blue point, and it gets the gradient of that contrast function, so it knows in which direction to change its output, so its green points get closer. So this idea of adversarial training, has had an enormous amount of success. These are completely non-existing fake bedrooms generated by adversarial net. This comes out of a paper called DCGAN that is a few years old. One of the authors is from Facebook. This is more recent work. This is a generative adversarial network that was trained on photos of celebrities. This work is from NVIDIA. It was published at IJCAI-ECAI this past year. These are non-existing celebrities. So basically, it's a deconvolutional net. So it's a convolutional net backwards, if you want. You feed it random numbers, and out comes an image of an alleged celebrity. And those are examples of what comes out. And they don't look like any of the samples in the training set. So it's pretty impressive. We can use those things to do video prediction. So this is what so this is more the idea of self-supervised learning. Without going into details, if you train with just least square, so you take a large convolutional net, you show it a few frames, ask it to predict the next few frames, and you train it with least square, you get blurry predictions. And it's because the machine cannot decide among all the possible futures which one to produce, so it produces the average of all the images that are possible. Okay, so you get a blurry picture. If you train with adversarial training, you get predictions like the one at the bottom. The first 4 frames are observed, the last 2 are predicted. This is another example where it's been trained on short snippets of videos from New York apartments. And as the camera rotates, it has to invent what the rest of the apartment looks like. And so it kind of invents the bookcase here at the bottom and the couch and everything. If you're interested in a self-driving car, it might be more interesting to work on videos coming from dashboard cameras in cars. And then this is some work also done at Fair Paris by Pauline Luc and Camille Coupry, where here we've run the mask RCNN engine on the images, and then we run a predictor, and the predictor tries to predict those maps of semantic segmentation. It can predict that, so here it's the same, the initial frames are observed, and then the last 3, I think, are predicted. And so it can predict that when a pedestrian starts crossing the street, it's going to keep crossing the street, and then a car in front of you is starting to turn left, it's going to keep turning left. And so that is very useful for a self-driving car to be able to predict what's going to happen. And the last thing I want to show you is latent variable models. So these are not adversarial training. This is another way of solving the problem of multiple predictions using latent variable models. And I don't have to go into details, but suffice to say that the architecture here is sort of an encoder-decoder architecture where you show an input to the system, it produces a code, then it runs through a decoder that tries to predict the future, for example. And of course, it can't predict the future entirely because there is uncertainty in it. So you introduce a latent variable z, which is additively combined with the code. And that variable z is some part of the time set to 0, some part of the time is allowed to be predicted from a deterministic function that takes into account either the observed future or the error, the prediction error. And so it's cheating a little bit, but it's a way of limiting the information content in the z. And one application of this is for self-driving cars, and I just want to show you quickly, if I can. Okay. So I should have removed those animations. So basically, you have one of those prediction system, and what it sees is an environment of the car that represents all the cars surrounding our car. So our car is in the middle of a little image, and we have some picture of all the cars around it, and as well as the speed and position of our car. And we're training a word model that given an action, which is a steering angle and acceleration, predict the next state, which is what the environment around our car is going to look like a fraction of a second from now. And we can use the real world, of course, for that. So if we train a direct deterministic predictor on this, we get this kind of prediction. So on the left is what happens in the world, and on the right is from the same initial condition what is predicted by this deterministic model. And what you get is this blurry prediction again. Okay, so bad idea. So now you can replace this with a latent variable model. If I can show it, here we go. And this latent variable model allows itself to kind of have a latent variable that will take up the slack that was not predictable previously. And what you see here on the three column on the right are different predictions for different sampling of the latent variable. And so these are completely made up, dreamed future scenarios from the system, from different drawings of the latent variable. And they all look reasonable. We don't know which ones will actually occur in the world, but they all look decent. So we can use those models for prediction and for planning. And I'm horribly out of time. I'm actually over time by a huge amount. So I'm just going to, if my presentation software allows me, I'm going to show you the last slide, or maybe not. Okay, I don't know if we probably don't have time for questions, so I may not be able to show you the last slide. The last slide was showing planning using this forward model to avoid accidents. So basically, learning how to merge into highways. And I apologize for the mishap here. Never install a new version of your presentation software just before I talk. Ooh, wow. Okay. All right. So, okay, let me show you my conclusion slide. Oh, this is not my conclusion slide. This is my conclusion slide. Okay, there is a question about intelligence. The quest for understanding intelligence, whether it's human or machines, is probably one of the biggest scientific challenges of our times, and possibly one of the biggest technological challenges of our times. And the next few decades are going to be very exciting. Perhaps it's going to take 30 years, perhaps more, to reach human-level AI. But one thing that's interesting is that in the history of science, there's been a lot of domains where the science has followed the technology. So the telescope was invented before optics was invented. Optics was invented to explain how telescopes worked and microscopes. The steam engine was invented before thermodynamics. In fact, thermodynamics was invented to explain the limits of heat engines. And it became a very important, very basic branch of physics. Aerodynamics was essentially mostly invented after the airplane. Not entirely, there was stuff before. But notions of stability and lift and drag and things like this basically resulted from the fact that airplanes were very practical. Computer science, of course, resulted from the invention of the calculator, and certainly information theory from the invention of telecommunication. So what is the equivalent of thermodynamics for intelligence? Is there a science of intelligence that we haven't figured out? That's my scientific project for the next decade and a half, perhaps, so they can do useful work in research. Hopefully, maybe a little more, we'll see. I'm really looking forward to this community to make significant contributions to this. Thank you very much for your attention. My apologies to the organizers for going way over time. Thank you.